So let's talk about where this pressure equation for hydrostatics comes from. And like a lot of stuff in engineering, it actually comes from Newton's second law. Sum of the forces equals mass times acceleration. So the forces that we're going to encounter in a fluid element are pressure, weight or body forces, and shear stress forces. And that's the sum of the forces. That's going to have to equal mass times acceleration. Well, we don't like to work in mass usually for fluids, so we're going to substitute in rho times volume for our mass. All right, and we're going to be talking about the forces at a point, and at a point that's a differential element. So the volume of that differential element is just dx, dy, dz. So we can plug that in and we end up with sum of the forces equal that. All right, so then what we do is just divide by dx, dy, dz, and we get it into a differential equation. Okay, it's quite a complicated differential equation. Rho times acceleration equals all of this stuff. These are your pressure forces divided by volume. These are your weight forces, and these are your shear forces. As you can see, it's from changing velocities. It gives you shear forces. And it has a mu in it, so you can tell that it's shear forces. All right, so this is our governing equation. We're going to use this. We're going to be solving this for a bunch of different cases over in Chapter 4, but it simplifies a lot for fluid statics. Okay, and again, it comes from taking a differential element and just applying Newton's second law. It's called Navier-Stokes equation. Actually has 3 components because you can see these are vectors here. So remember we had 3 components to our velocity vector: u times I plus v times j plus w times k. So you could put in a u and just for all your v's, and you get an x component velocity, and the same with v and same with w. So you actually get 3 equations out of this. And the same with acceleration. Acceleration is not simple in control volume analysis. It actually has 12 terms. We'll get into those a little bit more later. Okay, so there's again 2 primary forces acting on the fluid, pressure and shear, and these forces will cause a fluid to accelerate. In hydrostatics, things become simple because the fluid is not accelerating. So acceleration is 0, and not only that, if it's static, that means the velocity is not changing. It's not only not changing with time, it's not changing with position. Okay, so we're basically talking about a lake behind a dam where nothing is moving, right? So our dv, d whatevers, dx, dy, dz are all going to be 0. All right, so that simplifies it a lot. So all you have left is 0 equals this pressure forces and your weight, okay, or body forces, gravity forces. Rearranging this, you're basically just going to get rho times g is equal to this, what we're going to call pressure gradient vector. Okay, so that's a gradient vector times pressure. All right, and this is just a shorthand. This is a gradient. And it's a shorthand. It just means ddx times I plus ddy times j, and so forth. And you'll see those again in heat transfer, so we don't have to worry about them too much right now. Except for just have an idea of what that means. A gradient gives you the direction of maximum rate of change of pressure. So if you look at the equation, it's going to mean that pressure is going to change fastest in the direction of g when we're talking about hydrostatics. Okay, so as an example, let's say we have a fish tank. Okay, just sitting here. Static fish tank. Okay, so it's just sitting here. There's the water surface, and a lot of times what we'll do is put a little triangle to indicate that's our free surface. So up here we have air, and down here we have water. And that, again, is called a free surface. Okay. So if we look at our equation, what we're going to find is that pressure is going to increase with G here. So our gradient vector is going to go that way. Gradient of P. Same way G goes, right? Because G is acceleration of gravity, it's going that way. So we're going to get our maximum pressure here. Okay. Here, our pressure, call that 1, P1 is equal to P atmosphere. And notice that our whole free surface, the pressure is going to be P atmosphere. In fact, anywhere perpendicular to that pressure gradient, you're going to get a constant pressure. So pressure here is equal to pressure here. Okay, this pressure is different because we've gone down in the depth. So P, call this P3, is greater than P1. It's also greater than P2. Okay, so that's the hydrostatic case. Let's say we have that same fish tank and we put it in a car and accelerate it all together. So we put in an acceleration. Accelerating car. All right, so what's going to happen is now it's not the static case. We have an acceleration. So what is going to happen is this is going to be our free surface. Okay, it's still a line of constant pressure. P equals P atmosphere. But our gradient is going to go this way. All right, it's going to be affected by that acceleration. And our maximum pressure is going to be down here in this corner. Okay. And our lines of constant pressure are always going to be perpendicular to that gradient, like that. All right, so the accelerating car is not what we're dealing with right now. I just wanted to give you a picture of what that gradient means and how our lines of constant pressure are going to be perpendicular to that gradient. The coordinate system that we're going to use to make our lives even simpler than what we have up here. Remember, here's our equation. Rho g equals gradient P, or rho g equals this whole equation. Let's say g is just going in one of those directions, and usually what we do is we pick the k direction. Okay, so we say, or the z direction. G is going in the z direction, opposite this g direction. So g, the g vector, is actually minus the constant g times k. Okay, so the constant g is your 9.81 meters per second squared, or your 32.2 feet per second squared. So now plug that into our equation. This is what we have, and we can break it up into the components. Okay, so the k component over here on the left is the only component on the left, so that is the only one that is not equal to 0. These are equal to 0, and if you solve that, that just means that, well, pressure is not a function of x, and it's not a function of y. It's kind of like in our fish tank over here. It's only a function of z, okay? And in fact, it's a function of z with a very solvable little differential equation there. It started out pretty complicated. Because it's statics, it ended up pretty simple. So this is actually, since pressure is not a function of x or y, and normally in hydrostatics it's not going to be a function of time either, we can convert our partial differential equation to an ordinary differential equation, and this is one of the simplest forms of differential equations, because to solve it, what you have to do is just separate the variables. And all that means is bring the dz over to the other side of the equation, and then you're going to get the integral of minus the integral of rho g dz, that's that side, equals the integral of dp. All right, from 1 to 2, from whatever depth 1 and 2 is. Left side, the integral of dp is just delta p, right, or p. It's equal to p. Plug in your limits, and you get p2 minus p1. The right-hand side is just, it's the integral of rho g dz. So the right-hand side depends on rho and g. Now g, normally we can assume that's a constant, so that's going to pop out. If we're talking about liquids we're going to assume are incompressible. And incompressible meant constant rho. Yay! So we can just pull the rho out as well. And once we pull the rho and g out, then it's an easy integral again. So p2 minus p1 comes out to equal minus rho g z2 minus z1. Okay, and that's where our equation is coming from. Rho g again was equal to the specific weight, or gamma, so we can also plug that in. So some things to remember, and let's look at this particular figure here, and you're going to use this figure in your notes quiz as well for the next few problems. At the free surface, the liquid pressure has to match the gas pressure, okay, because this is at a point, and you can't have two different pressures at the same point. Okay. So P at z equals 0, if you put z equals 0 right there at the surface, which we like to do a lot of times, that's going to be equal to P atmosphere, whether you're in the air or whether you're in the fluid, in the water. And another thing to remember is container shape doesn't matter. If you look at this equation, delta P equals minus gamma delta Z. So the only things that are in those equations that are going to determine what the pressure is which fluid it is, or fluid property, which is a specific weight, and the depth. Okay, so it doesn't matter what kind of shape the container is. So go ahead and answer quiz questions 3 through 5, and those questions are going to be based on this figure. So when it talks about little a, b, c, etc., it has to do with that figure.